In this section, we'll be talking about correlation and simple regression. Correlation is a relatively intuitive subject. We look for correlations or patterns or relationships all around us all the time. When we notice these two events are related or associated, for example, as prices go up for a product, the quality also generally increases. Or as the prices go up for a laptop computer, the weight generally goes down. Taller people get paid more in organizations, and pay increases with height. This is kind of an interesting subject. The strength of this association varies. The relationship between performance and promotion may be weaker than between performance and termination. But there's two things that we want to quantify or formalize when we talk about correlation. We want to talk about the relationship, whether it's a positive or a negative relationship, and then we also want to talk about the strength of that relationship. In correlation is just the extent to which two variables covary or move together. We will be using the Pearson correlation coefficient. This Pearson correlation coefficient ranges from a -1 to 1. Negative meaning that it's perfectly inversely correlated, and 1 meaning that there's a perfect positive correlation. I have several examples here that exhibit the correlation between two variables. When two variables are perfectly correlated, when one goes down, the other one goes up, and vice versa. And so that is found here in the first graph. Let me get my pen. Pen isn't quite working today. In the second, we can see that there's some variation. So you might imagine that there's a number of these data points in this, such that we couldn't perfectly predict one variable to the next, but we can see that there's a relationship. If you can kind of sense that there's a line that would go through that data. In the middle example, there's no relationship. If I were to pick an x at any given point, it wouldn't correlate with any given y. You know, an example I commonly use in class, I probably need a better example, but if we took a look at the temperature on any given day and counted the number of red cars in the parking lot, we wouldn't expect that the number of red cars and the temperature would have any direct relationship or correlation. Then as we move into the positive range, we can see less than a perfect positive correlation here in this fourth example. And then finally a perfect positive correlation, meaning that as x goes up, y goes up by the same magnitude. So what is the correlation between personnel appraisal and salaries implied by the following statement? Now we'd assume that if the appraisal is high, we would expect salaries to go up. In Company X, of those employees who received a good performance evaluation, 100% got raises. Well, that kind of implies this perfect correlation. But we probably wouldn't find that the correlation coefficient is 1 or perfectly positive, because the magnitude of those raises, even though all of them received raises, might be different. The R, or in Greek the rho, is not racially scaled, so R is 0.8 is not twice as high as an association with an R of 0.4. We need a racially scaled measure, so we look at R squared, and we'll talk more about R squared when we get into regression. The R squared is the proportion of shared variance between two variables, or how much of one variable, the variation in the variable, is described by the variation in the independent variable. So when we have an R squared of 0 and a correlation coefficient of 0, we can see that there is no overlap. There's no relationship. So that's kind of that example of blue cars and the temperature. In the second example here, we see that there is overlap, although it's not perfect. So we can say that there's about 25% of y that is described, the variation in y is described by the variation in x. Then we move up and we have a higher correlation. So it might be negative or it might be positive. When we square the correlation coefficient, we could say that, once again, about half of the variation in x is described, or the variation in y is described by the variation in x. And then finally we get to a perfect correlation, which means that all of the variation in one variable is described by the variation in the other variable.